So hello everyone. So in the last session we were discussing about the complete solution. In today's session we are going to continue with the same thing with the complete solution. We are going to see the different forms of complete solutions. So what we had discussed in the last tutorial was that how to find the complete solution. So by adding the particular solution, that is xp, and the null space solution, that is xn, we get the complete solution, that is equal to x. So how do we find XP? Let me quickly revise this. So we'll find XP by XP is nothing but a particular solution. So there what we have is the pivot columns as well as the free columns. So we'll make the free columns as completely 0, and then we'll find the solution with respect to the right hand side, that is the B vector. So if I write here, so XP, we will find the solution with respect to the B vector on the right side here. So then we'll try to find what is our XP. So whereas in the XN case, so this is not the right way, so let me write it correctly. So how do we find the particular solution is that we'll consider that AX equal to B. So then we'll find the particular solution, whereas in the null space solution we'll find, we'll consider that AX is equal to 0. It means the right hand side we'll consider it as 0. Then every alternative free variables will make it as 1, and then we'll find the special solutions, and that is how we're going to find the complete solution by adding the particular solution and the complete solution. So now we will look into one more example here. So the speciality of this example is that the number of columns are more when compared to the number of rows. So let me write that example here. So suppose, for example, if it is given the matrix A, that is of form 1 1, so 1 and 2 and minus 2 and minus 3, and the B, the right hand side, here the given are the vector as the general form, so that is B1, B2 and B3. The values are not given, it is given in a general form. So now we have to find the complete solution. So how do we find the complete solution? There are two ways. So what we can do is we can go with the augmented method, or we can just consider this AX equal to B, and then we go for the row elimination process. So anyway, we can do it anyway. So let me go with the augmented method here. So if I go with the augmented method, then my matrix will become 1 1 B1, then it is 1 2 B2, then it is minus 2 minus 3 and B3. So this is my augmented matrix here. So now if I go with the row elimination, so I have to eliminate this second variable here. So I'll just subtract this, no multiplier is required because it is 1 and 1. So after that I'll get the first row as it is, whereas the second row I'm going to subtract. So this will become 0, this will become 1. So here this will become, so it is B2 minus B1. So you note here, so because we are subtracting the second row from the first row, so it is B2 minus B1. So likewise we will repeat the same process for the third row. So then here we'll multiply with the minus 1, and then we're going to subtract it. So then minus 2, so this will become 0. So here I'll get minus 1. So here I'll get this as B1. Sorry, it is B3. Then I'll get here B3 minus of minus, I'll get plus 2B1. So this is the solution for this. So now I have to eliminate this, because the pivot in a column can be only one pivot. It cannot have the two pivot values here. So if I go with the further reduction here, so then the new row is 2, I'm going to subtract with the row 3. So then I'll get that as, that is 1 1. So here I have the row 1 as it is, and row 2 remains as it is, that is B2 minus B1 here. Then I'll multiply with minus 1, and then I subtract. So then I becomes 0. So here when I subtract, I'll get here, that is B3 minus, sorry, B3 plus 2B1. So minus of it is multiplied by entire term by minus, so it has become minus b2, and it is plus b1. So if I just write this rearranged terms, so I'll get here, so b1 it becomes so cancel it, so I'll get here plus b2 and plus b1. So because one of b1 it get cancelled, so I've just rewritten this below, so please do not consider it as one more row, it is just a rewritten form of that. So this is the final value of this. Now what is the, for this case, what is the particular solution and the null space solution for this case? So let me rewrite this, the final equation here. The final equation which we got is, we have the space here, so I'll write here. So we got 1 0, then the final equation. Okay, this was not final, sorry, we have to eliminate this as well. So to eliminate this, again we will subtract, we will add this with this, we're multiplying with -1, so I'll get the final equation as that is 2b1, this is 2b1 minus b2, then this is 0 1, this is b2 minus b1, and then this is 0 0, and this is b3 plus b1 and plus b2. We can write however we want. So this, whatever the third column is there, this third column is nothing but the augmented column, so we can take it to the right side. So now to solve this, the null space, to obtain the null space, that is xn, we can consider this as equal to ax equal to 0. So when we consider ax equal to 0 here, the null space is actually 0. You know why? Because if I rewrite this matrix here, so then it will be something like this. Then if you see the third row is completely 0, so it means 0 is equal to 0 here. So this is 1 0, this is 0 1, which is on the A, and then here I have my variables, that is x1 and x2, which is equal to, now the right hand side, I don't want to rewrite all these equations, so that you can consider. So all these things that comes on the right hand side. So now if you look into that, there are no free variables. When there are no free variables or no free columns in this case, so when we consider the right hand side is equal to 0, since there are no free columns, therefore x1 and x2 is equal to 0. So how do I get the right hand side which is equal to 0? Only when x1 and x2 is equal to 0. So therefore the special solution for this case is 0 comma 0. And the particular solution, what we get is that the particular solution is nothing but, by considering the b, we have to get this, so we will get the same terms. So let me erase this unwanted portion here, because this already we got the final solution here. So if I remove this, then the xp, the particular solution we'll get here is xp by considering ax is equal to b. So ax is equal to b, so third row anyway it's going to be vanished because it is completely 0. So here I have to get this, so the x1 and x2 should be the same value as whatever is there on the right side. Therefore the complete solution x is nothing but it is xp plus xn, and that is equal to 2b1 minus b2, and the second component is b2 minus b1 plus, let me erase this part here, so because this is not required now. So plus, so what is there, the what is xn? Xn is completely 0 0. So now if you see here, so this we call it as the full column rank. So full column rank is nothing but it is a general form. So let me write here, this is in a form of full column rank. So it means that, so R is equal to, it has the identity matrix and as well as the 0 rows. So if you look into this solution here, so we have the identity matrix and below that we have the 0 rows. So that is what it represents, and which is equal to, so here we can write it has M cross N identity matrix, it has M cross N identity matrix, and M minus N zeros, rows of zeros. So rows of zeros, if you're right. So if you look here, so what is the dimension of this matrix? It is actually a matrix is of 3 cross, it is a 3 cross 2 matrix. So now in that, let's see whether it satisfies this condition or not. So it is it's not M into N, it is N into N. It is N into N identity matrix. Yes, perfectly. Now what is the value of N? So this is N. So N into N, it is 2 cross 2 identity matrix, and M minus N. So what is M? So 3 minus 2, it is 1. So it means there is a 1 row with 0 rows. So there are quite few properties of this full column rank. So we will see full column rank matrix. Let me save this page and go for the next one. Page not in this. Okay, so let me take the new page and write the properties here. So every matrix A with, let me make this bold, full column rank, that means R is equal to N. So what is the R value here? What is the rank of the matrix? The rank of the matrix from the previous example is 2, because we have the pivots, the number of pivot columns are 2, so that defines the rank of the matrix, and that even the column is also 2, so therefore it is R is equal to N, has certain properties. So the first property is all columns of A are pivot columns. So all columns, if you look at the previous example, there are no free columns at all. It is all the pivot columns which we had. So both the columns are pivot columns. So it means the first property is satisfied. And second property is that there are no free variables. So that's what we have discussed just now. Or special, if there are no free variables, there are no special solutions. No special solutions. Third one, the null space N of A contains only 0 vector x equal to 0. So the null space contains a 0. Now what is the value of x and x1 and x2 in the previous case? The value of x1 and x2 in the previous example is 0. So it means it has the 0 vector. So the fourth property is if Ax equal to B has a solution, then it has only one solution. It has only one solution, that is particular solution. So hope you have understood this. So next we'll talk about the independent columns and other things. So now we will look into the another case of the complete solutions where the rank of the matrix is equal to M. It means the number of rows. So let's talk about that. So I'll save this page here. So page not 1. So this also we call the title as the complete solution, but with respect to the bracket I'll write, so R is equal to M case. So if R is equal to M, this is also called, that is a full column rank, the previous one which we called. So the next one means this one whichever we are talking about, this is called as a full row rank. The full row rank means that the R is equal to M. So let us take an example to understand this. So here there will be more number of columns than the number of rows, means the value of N is greater than M. So then it is called as a full row rank. So let's take an example here with the linear equation, that is x plus y plus z equal to 3 and x plus 2y minus z equal to 4. So now here the rank of the matrix R is equal to M is equal to 2. That is what here rank of the matrix. So now let us look into the solution of this case. So let us write the matrix A, let us write the augmented matrix here, and then we will go for the row elimination and row reduction method. So here the coefficients are 1, 1, 1, and I'll write the augmented here. So that is B. So B I'll write in red, and here I have 1, 2, minus 1, and the B value, the second B value is 4. So this is augmented. Let's go for the row reduction. So now I have to remove this. To remove this I have to subtract. So let us subtract this. So first row will remain to be as it is, 1, 1, 1, 3, and this becomes 0, 1. So this will become minus 2, and this will become 1. So now if you see, we have the two pivots here, that is here the 1 and this 1. So now we have to remove the values above these pivots. So to remove the values above the pivots, we have to multiply and add with the above rows. So if you do that, so that is multiply by minus 1 and add it. So then I'll get here 1, 0. So if you multiply this minus 1 and add, so this is 2. So minus 1, it will become plus 2, so it will become 3 here. So this is minus 1, so this will become 2. So the second row as it is, so it is 0, 1, it is minus 2, 1. So now we have come to a reduced form and identity matrix. So sorry, I'll not put here, so that will leads to confusion. So now this is a special case here again. So what about the particular? So how do we find the particular solution in this case? So let me copy this and I'll rewrite there again. I have copied this, and yes. So this is our case. So how do you find the solution, the particular solution? So if you write this in a form that this is x1, 1, 0 plus x2. If you write in a form of vector, then it is like this, then it is 0, 1, and whereas the third column is the free column here, so x3, then I have that is 3 and minus 2, which is equal to then 2 and 1. So for a particular solution, we know it is the form of ax equal to 0, sorry, ax is equal to b. So in that case, the free variables will make it as 0. It means we'll make x3 is equal to 0. So when we make x3 is equal to 0, so this column vanished, so we have this. So now what is the particular solution that we will get? So we will get an xp is equal to, so it is 2, so I'll get here, so 2, 1, so x2 is 1 and the x3 is 0. So now the next we will find the null space solution. To find the null space solution, so there is one free variable, so we'll find the null space solution by considering ax equal to 0. So if I rewrite this entire thing, so let me copy here. If I copy this entire thing and if I write here, so then what happens is that this entire thing gets deleted. So this term will come to the right side here. So it comes your right side. So let me erase these unwanted terms here. So this x3 has become 1. So for this to be a 1, so what is the special case here is that, so then xn, the special solution is that, so this should be minus 3 because it has come to the right side, so it has become minus, so it is minus 3, it is minus 2 and 1. So this is a special solution. So the answer, the complete solution for this case is, if you write here, that is x is equal to xp plus xn is equal to, then we have here the same thing we can write. So you can write it, so I'll leave it to you to write. So so just cross verify whether it satisfies both these conditions, whether it is equal to ax equal to 0 and ax equal to b. So now ax equal to 0, so if I add all these values, that is if I consider here that uh, with minus 3, so here I have 2 plus 1. So if I multiply this 2 with this matrix and see whether it is perfectly matching, yes. So if I multiply this column vector by 2 and this with 1, I'll perfectly get this 3 here. Forget it. I will not go in much of this confusion. So we just define that the complete solution, that is x is equal to xp plus xn. So here then finally we can write that this is xn. So then this is equal to, that is nothing but we have, that is 2 1 0 plus x3, that can be written as minus 3 minus 2 and 1. So now it has certain properties as well. So to write the properties, we'll go for the next page. Let me save this here. So we'll define the properties of this a full row rank. So let me write that here. So it is similar to the previous column rank, the full column rank matrix. So every matrix A with full row rank, that is R is equal to M, has certain properties. So that properties I'll write here below one by one. So first one is that, so first property is that all rows have pivots. All rows has pivots and R has no zero rows. So this is the difference with the full row rank and the full column rank. In the full row rank, all the rows has pivots because there are less number of rows, so all the rows has pivots and there is no rows with the 0. So the second property is that Ax equal to B has a solution for every right side B. There's another property, and the third property is that the column space is the whole space, that is R power M. So we can read it as R power M. And the fourth is that there are n minus m equal to, sorry, it is n minus R equal to n minus m special solutions in the null space of A. So this is the, so these are the four properties of full row rank. So now we will see the linear independent case that we will discuss anyway later. So what are the four possibilities for the linear equation that depends on the rank? So this is another case here. So let us write here the four possibilities for linear equation depend on the rank R. It is go like this. So for the first one is that, so R is equal to M and R is equal to N. If R is equal to M and R is equal to M, then that will result in the square and invertible. When it is resulting in square and invertible, then we have the solution Ax is equal to B has only one solution. So this is the meaning of it. It means if the rank of the matrix is equal to m and also the rank of the matrix is equal to n, then it definitely it has to be a square matrix, because only for a 3 cross 3 matrix, 4 cross 4 matrix, and if there are no 0 rows, then the rank of the matrix remains to be as the same as m and n. Then it has only one solution. So that is the meaning of it. So if the R is equal to m and R is less than n, so it means if there are more rows than columns, then it is, we call it as the short and wide matrix. We call it as a short and wide matrix because there are more rows and a less column. Uh, Sorry, my mistake. So if R is equal to m and R is less than n, it means there are less number of rows and more number of columns. So if there are more number of columns, so it is, you can think of just like a 2 cross 4 matrix, 2 cross 5 matrix, where there are 2 rows and 5 columns or something like that. So then the rank of the matrix remains to be like which is equal to the row and the columns are more. So it is, the rank of the matrix is less than the number of columns. So that kind of matrix is a short and wide matrix. So then the solution will be, for Ax is equal to b, has infinite solutions. So I'll just write infi solutions to represent infinite. So if you consider the next case, that is if the rank of the matrix is less than m and if R is equal to n, means the other case when the number of rows are more and columns are less, then it will be resulting in the tall matrix, tall and thin matrix. Definitely there are less number of columns, so you will get, and more number of rows, you will get it something like 5 cross 2 matrix, 5 cross 3 matrix. So there are, it looks like thin and tall. So then the solution for Ax equal to b has, either it will be having the 0 or 1 solution. And for the next case, when R is less than m and R is even less than n, then it is a kind of, it is not a full rank. It is neither a full column rank, neither a full row rank. So then its solution Ax is equal to b has 0 or infinite solutions. So these are the few points that we have to remember it when we are talking about the rank of the matrix and when we are correlating with this.